What is the difference between MREL's VOD recorders and the ShotTrack VOD 305? Thank you for your question. Similar to MREL's VOD recorders, the ShotTrack VOD 305 is a continuous type of explosives VOD recorder. However, unlike MREL's VOD recorders that use factory-calibrated precision resistance cables, the ShotTrack VOD 305 uses the time domain reflectometry technique. The short form for that is TDR. It's used for determining the length of a consumer-grade coaxial cable. It sends an electrical pulse down a coaxial cable and waits for the reflected signal from the end of the coaxial cable in the explosives to return. The ShotTrack VOD 305 records the total time it takes, starting from when the pulse is sent until the time the reflected pulse from the end of the cable arrives back at the recorder. If one knows the speed of that specific pulse in the cable being used, then one can easily calculate the length of the cable. The TDR technique used by the ShotTrack VOD 305 is not new technology. In fact, TDR was not initially intended for use in explosives at all. It was developed by Los Alamos National Laboratory in the mid-1900s. It was developed to measure the position of a shock front along the ground from a nuclear explosion. Those blast pressure waves are magnitudes slower than explosives detonation velocities, so the TDR technique's relatively slow maximum recording speed was suitable for Los Alamos's intended application at that time. As an aside, Los Alamos uses MREL's VOD recorders when testing explosives VOD. There was an earlier commercialized TDR-based recorder called the VOD-R that was marketed as an explosives VOD recorder. It was manufactured by EG&G in the USA, and it was in use in the 1970s and 1980s by the industrial explosives industry. It was essentially rendered obsolete by the subsequent development and commercialization of MREL's resistance-based VOD recorders in the early 1990s. To more fully answer your question, I thought I'd take this time to provide my understanding of the problems and limitations associated with explosives VOD recording using the TDR technique. First, I'll summarize some of the key limitations of the ShotTrack VOD 305 when compared to MREL's VOD recorders. It is unsuitable for testing VODs in explosive samples. It has a relatively slow recording speed. It has a relatively short maximum length of VOD recording cable that can be used. It has a requirement of the operator to self-calibrate the cable used, and the cable used is heavy to handle. Okay, I'll explain further. The ShotTrack VOD 305 does not have the capability to test the VOD in explosive samples. With an advertised recording speed of only 256,000 samples per second, its recording speed is far too slow for that application. Now, to ShotTrack's credit, it is my understanding that ShotTrack does not advertise use of their ShotTrack VOD 305 for testing explosive samples. MREL's recorders all record a change in resistance with time. Unlike TDR, resistance measurements are instantaneous and can be performed at any time, and accuracy is only limited by the recorder's recording speed. In contrast, the TDR technique is limited in its maximum recording speed because it has to wait for the reflected signal from the end of the cable before it can send another signal. In the intervening time, no data can be collected about the VOD of the explosives. As a result, even the world's most affordable continuous explosives VOD recorder, MREL's HandyTrap 2 VOD recorder, records at about 4 times the speed and data points per meter than the ShotTrack VOD 305. The world's most popular continuous explosives VOD recorder, the MicroTrap VOD data recorder, records at 8 times the speed and data points per meter than the ShotTrack VOD 305. The world's most capable continuous explosives VOD recorder, the DataTrap 2 data VOD recorder, records at 40 times the speed and data points per meter than the ShotTrack VOD 305. Now, the ShotTrack VOD 305 has a maximum cable length limit of 300 meters. This includes the distance from the bottom of the first blast hole being monitored back to a safe location of the recorder itself. Contrast that to MREL's MicroTrap, for example, which can use up to 1,000 meters of VOD probe cable LR blue in multiple blast holes per blast, plus a practically unlimited length of coaxial cable back to the safe location of the recorder. This shortcoming of the ShotTrack VOD 305 could be a huge problem in some of the larger energetic blasts, where the recorder may need to be located a long distance from the blast to protect it against fly rock impact and thus recorder destruction. The user of the ShotTrack VOD 305 must calibrate the VOD cable being used before each test. This is to determine or confirm the speed of the ShotTrack VOD 305's signal in the cable, as discussed earlier. It is recommended by ShotTrack that 300 meters of cable be unspooled and pulsed by the ShotTrack as the calibration procedure before each test. But how is the operator to know that he has exactly 300 meters of cable attached to the ShotTrack during the calibration process? Is the operator expected to measure it physically? Also, if a box of consumer-grade coaxial cable says 300 meters on the box, it doesn't necessarily mean there's 300 meters in the box. If the box, for example, contains only 270 meters and not 300 meters, and the operator tells the ShotTrack VOD 305 that it's testing 300 meters during the calibration procedure, then the ShotTrack's VOD results will be off by a whopping 10%. It seems an involved process and potentially subject to error. In contrast, MREL's VOD probe cable is provided factory tested and factory calibrated, ready to use immediately. The weight of the cable used in the ShotTrack VOD 305 is about 5 times heavier than that used by MREL's VOD recorders. That's the VOD probe cable types. So that's approximately 50 kilograms weight versus 10 kilograms for 10,000 meters of VOD probe cable. Now, in summary here, ShotTrack markets its ShotTrack VOD 305 as the next generation of velocity of detonation monitors. I believe the phrase next generation is better left to advancements in technology, not repackaged old TDR technology from the mid-1900s.